First off, any questions from homework stuff? I love you guys. Let's see. Wait. Yes?
Number 53 on
53. Ooh, yeah, I like it. Oh. Let's see. 53, here's what the problem is. They give you this really freaky looking little equation.
What section?
3. Number 53. There's 2y. And this is called, not surprisingly, this is called a differential equation, Scott. Differentiated is another way to say, if I say take the derivative, another way to say that is differentiate this. So this is called a differential equation. Things in the real world involve rates that are related to each other. Like this is the first derivative, this is the second derivative. So it could be like water flowing, and the flow is increasing, and that's changing how quickly this thing and changing how quickly the electricity is being made. So there's relationships between different levels of derivative. Really kind of cool. In fact, there's a course called Differential Equations where we learn how to solve this. Now that's not what this point of this course is. We're in 180, not 285. Holy shit. That would be differential equations. All they asked me to do is figure out what A and B are so that this solves this equation. You notice how I know what y is, so I can plug that in there. What else do I need to know? Y prime, so figure out what y prime is, plug it in. And then of course I also need y double prime, so figure out what y double prime is and plug it in. So this is almost feeling like algebra, really. Just figure out what you need, plug it in. And then you can solve for A and B. You gotta try. Looking at your faces, I don't think a lot of us have tried this one yet. Have any of you tried this one yet? Well, then I ain't gonna say much more. You wanna try it right now? You wanna try it right now?
Yeah.
Good, try it, do. Y prime equals y double prime equals, create the stuff that you need for the equation. A sine x plus b cosine x. Yeah. Hopefully you're going off the book and not what I wrote. A sine x plus b cosine x. If you think about it real quick. I know you're in the middle of doing this. How is the only way, do you see how in order for this to equal sine x, these all have to be like terms? Right? So one possibility could be e to the x is its own like terms with its own derivative, but how in the world would a bunch of e to the x's make sine x? So do you see how cosine and sine, they are like terms with their several derivatives? Pieces of them are, right? So that's like terms with this, and that's like terms with this. And now it's going to turn around again for this one. You have all these like terms running around. If a and b are the right numbers, it would make this work. That's kind of like the idea, part of the idea of differential equations is that. What do we get here? We get negative a sine x minus b cosine x. And then you throw all that stuff in there. This feels a little bit like partial fraction decomposition. I don't know if you guys remember partial fraction decomposition, but it's going to come up very soon. That's this part. And this part. Finally, minus twice y is supposed to equal sine x. So I get all my like terms together. I get negative 3a minus b sine x. Right? Negative 3a minus b sine x. And then I get negative 3b plus a cosine x. All right, is that cool? The derivatives are relatively easy. You plug them in the equation, get your like terms together. Okay. Is that decent so far? I mean, was that hard? Was that difficult? It's easy derivatives. Why are we doing these? Because the equation needs them. Right? So then we throw it in the right places. We get our like terms together. Now, what the hell's the next step? What must negative 3 minus b equal? No, well, sure. So the coefficient of sine x has to be 1, and the coefficient of cosine x has to be, are there any cosine x's? No, so this better be 0. Get a little system of equations. Oh, shit. So negative 3a minus b must be 1 because I have 1 sine x. Negative 3b plus a must be 0 because I ain't got no cosines over there. And then you just have to solve that system of equations. Okay. You guys can finish that out. It should be easy as all hell. It has to be. This is not easy, that's a problem. This part here? Easy. Yes. Say again?
How'd you get the 1?
So in order for this side to equal that side, that's got to be a 1. That's where 1 sine x would have come from. And that, whatever the hell it is, has got to be a 0. Because I have no cosines over there. Yeah. So if there would have been a 3 in front of the sine, that would have had to equal 3. Okay. Any other questions from homework?
Yeah.
Yeah.
3.1, number 64.
Oh yeah, this is awesome. When you first read through this one, you're like, okay, wait a minute. Both? What do you mean both equations? So you have a parabola x squared plus x. Everybody got what they want from this here? We understand it's not done yet. Finish that. So you have y equals x squared plus x is the function we're working with. And I want to find the equations of both lines that are tangent to this going through, what was it? 2, -3. So if you kind of graph this just to get a feel for what's going on here, so you got 2, -3, 2, -3. That's the point we're talking about. And x squared plus x. If you factor that, it's got 0 and -1 as right x plus 1. So the vertex will be in the middle here. So this one looks like. So it's going to be, let's see, this is going to be interesting. There's going to be a tangent line here that goes through there, right? And somewhere there's another tangent line, probably up here somewhere, that also goes through there. There's a tangent line somewhere that goes through that. Probably much further along, we're going to find both. You guys get this idea. So, you know, this is kind of a gross graph example, but if I had a parabola and I had a point, there's going to be one tangent line there and another tangent line there, possibly, right? This is just a little skinny little dude. It's harder to tell. It's probably way the hell up there, but still. That's how it means there's two tangent lines going through that point. Is that cool? Because it curves. Yeah. So how do we start this off? How do you find the tangent line? What's the point? What is this point on the curve? What is that point? What's that point? An appropriate response would be, I don't frickin' know. Awesome. Give it a name. Let's say that it's XY. Sounds exciting. Now to be more specific, it's the point X comma what? What's Y? What's Y?
X squared.
Yeah, X squared plus X. Okay, so that's the point. And then what's this point? This point is 2, -3. So, all right, I'm going to try to not do this whole problem for you, but give you enough to think about. Can you find the slope of this period? Yes. In order for this line, the tangent line, to go through this point, what slope must it have? For this point example, what slope must this have? In fact, don't you know this point? Yes, it's the point 2, -3. Don't you know this point? Yes, it's the point x comma x squared plus x. We're in Math 1A. You get to the point where we're like, how much did Catherine make? X. I know exactly how much she made. She made freaking X dollars. And we can work with the shit, right? So what 2 points do I have here? That point and that point. Beautiful. Can you find the slope between them? Yes. You can also find what the slope is by taking the derivative, right? Yes. I'm going to do something with those two things. I should have given you enough to realize how to think about this problem. I don't want to do this problem for you. Somebody give me, well, all right. What's the slope just from this? Backward? Yeah, okay. 2x plus 1. That's what the slope is at any point. X, right? What do I want the slope to be? How do you find the slope between any 2 points? y2 minus y1. So it'll be x squared plus x minus -3 over x2 minus x1 So that is the slope at any point x. That's what we want the slope to be. So what do you do with these? Yes, that is what the hell a slope is. That's specifically what we want it to be for this problem. So we set them equal to each other because then we can figure out what x makes the slope this. That'll give me now, it's going to give me two answers because it's freaking quadratic. And that's why there's two tangent lines. One's going to have a negative slope and one's going to have a positive slope, more than likely. That's what it looks like to me, but maybe my picture's so far off, who knows. But you're going to get two answers. I know when you first read through that, you're like, what the shit am I supposed to do with this? But you have got to start playing around with stuff. There are two ways to get the slope. One is the calculus way, the new shit, and the other one's old shit. So this is a beautiful example of using new shit and old shit together. Sorry, sounds like farming class. Yes?
I'm sorry, but I mean, if we were to just use the derivative, I feel so dumb for asking that, but like how I use it to solve it. So you said that that's two ways to find it, right? So the old way, which is the end.
True, but I need both to make this problem work. I know what the slope is at every point on this graph. And I know what I want the slope to be at the 2 points that work. So then I set these equal to each other. They have to work together. Yeah. It's the same thing, I mean, it's exactly the same thing as any word problem, which every student in the world hates, which every student in the world needs to get the hell over it. If I have a rectangle where the length is 4 more than the width, the area, no matter what the shit it is, will always be x squared plus 4x. It just is. Just like that's always the slope. That's always the slope anywhere on this curve. There it is. There's the slope. If I want specifically the one where the area is, 12, then I'm going to set that equal to that. To force to see what x makes that happen. That is exactly what the shit's going on here. I'm not saying you're supposed to read this and know exactly how to do it. I'm saying that's the exact same idea. This is every rectangle that has this happen. Then I want a specific one. This is every slope at every point. This is what I specifically want to have happen. Man, I love that problem. I don't know if you guys can tell. But this is where, 176 should have given you a little taste of this, but now, I don't know if I've said this yet, but math starts at calculus. Now you've got to realize the problem could be anything. You just have to figure out how to use what you know to get the problem going. You can't look at example 7. Example 7 shows you no, there's no freaking example like this. So it's all about the idea and how does the idea apply to what they tell me. You have to start thinking like that, not looking for examples, not saying I've never seen anything like that. No, you haven't, but you know the idea behind it. Or hopefully you do. All right. Anything else from homework I can help you out with halfway? This one you're basically done. The rest of this is algebra, right? Yeah. Anything else from homework stuff? Okay, all right. So let's do the one thing we have left to do. And really, the one thing we have left to do, this to me is one of the most interesting things. And I love it. You're all like, that doesn't mean anything to me. I had a problem my junior year math proficiency exam to make sure that I could keep going to get my degree. It dealt with this function. I think this function showed up in the homework early with a limit question. If you think about this function at all, just think about what it does, it'll freak you out. It has to. If x is positive, there's no problem with it, right? 1 to the first, 2 to the second, 3 to the third. What happens if x is negative? What might happen? Like, what if x is negative 1/2? What's the problem with that? Again, we're dealing with real stuff, real numbers. This would be trying to take the square root of a negative number, right? It would be negative 1/2 to the negative 1/2, which is 1 over the square root of negative 1/2, which is not real. So you guys see. But what about negative 1/3? It's fine. Negative 1/4? No good. Negative 1/5? Fine. Negative 1/6? No good. 7/2? Negative 7/2? No good. Negative 7/3? It's fine. Holy shit! It's like, where is it continuous? I think was the question I had to deal with. I can't remember. This thing is insane. It's funky-delic. But what we're going to do instead of talking about where is it continuous is take its derivative. And here's why we need a new way to do this. There are two competing rules here. What do I do with some x to some number power? How do I take its derivative, of course? No problem. What if I have a number to an x power? How do I take its derivative?
ln base.
Yes. So the thing ln base. That's why e is its own derivative, blah, blah. Two completely different rules because they're completely different functions. The variables in different places. Totally different functions. All the students trying to make them the same. I got both of those happening at the same time. Which rule do I use? Shit. So I can't. It's not in the form of either one of those. It's sort of like both and neither, sort of like Schrodinger's cat kind of thing. Depends how you look at it. What's really cool, I love this so much. You're starting to realize when I say that, you're like, I'm going to hate this so much. No, you won't. This is not a hard thing. If I have a variable expression raised to a variable expression, here's how to deal with it. What do we normally do when we have variables up there? But we did this the other day. Take natural logs both sides. Because we know implicit differentiation now. I can do shit to the function, take implicit differentiation, and solve for dy dx, solve for y prime. That's awesome. That opens the door to all kinds of weird shit like this. This is weird shit. So I take the natural log of both sides. Go ahead and take the derivative of that. So it involves implicit. This side is going to involve what rule? X times natural log of x, so it's a product rule. I like it. All right. So what's the root of a natural log of y? 1 over y. Y prime. I love it. Chain rule, implicit. I love it. Side, not too bad, right? Derivative of that, so that I just get ln plus x times the derivative of ln x. It'll be x over x. 1. Multiplied by y, and since it's not truly implicit, we have an explicit function. This is beautiful. I know what y is. It's x to the x. So I'm going to multiply both sides by x to the x. I get x to the x, natural log of x, plus x to the x. Right? That's what y is. So when I multiply by y, I'm really multiplying by this. Now, let's see if anybody is anywhere near as excited about what I'm about to say as I am. I normally can bank on that being a no. Well, let's see. This kicks so much ass. And it's relatively recently that I realized this. Nobody ever told me this shit. And I'm like, damn, I'm going to tell everybody this shit. If I look at this the wrong way and I look at it as x to a power, then you would bring, how would you take its derivative? You would bring the x down times x to the x minus 1, right? Can somebody help me out? What is that, though? Aren't they like bases? So what do you get? You get x times x to the x minus 1, you get x to the x. Right? You add powers, is that cool? Yeah. All right, now what if I look at it the wrong way as a number to x? Like a to the x. It's itself times the natural log of the base. Do you notice how that is a combination of both ways of looking at it? The problem with this was it was two rules at once. What's so cool is it's a combination of both rules. So beautiful. Nobody ever told me. I don't even know if my teachers even knew that shit. Yeah, as I expected. A few guys are like, okay, and some of you guys are like, whatever, man. Just tell me what to do with the shit. Hopeful. So, let's see. Let's do one a little more interesting. Blah, 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 blah. Here we go. Yeah, I like it. You guys try this one. All right. This one should be really quick. I'll tell you why. So, where have you guys gotten to? What point are you at? You're like, I wrote down the problem. All right, shit.
Change the radical to 1/2.
I love it. Okay, so you can work with the problem, the function ahead of time before you start taking derivatives, right? And of course, what do you do with those?
X over 2.
Yeah. So then when you take natural logs of both sides, what happens? You just get, right? Which is half of what this was. So that guy's derivative is going to be half, in a sense, right? So if you do this, keep going, you get 1 over y prime equals, again, so it can be half natural log of x plus x over 2 over x, which is exactly half of what this was. All right? I mean, so it's going to be half of what the other function was. What's up? So be cool. What's up? So derivative of x over 2 is 1/2. Derivative of ln of x is 1 over x. It cancels with that x. You just get 1/2. So then when you multiply by this, let's multiply by this, you'll get 1/2 x to the x over 2 ln x plus 1/2 x to the x over 2. So it's basically half of this with the power the way it should be. All right, so that one wasn't overly exciting. So here's a good one.
I'm sorry, for 1/2 natural log x plus 1/2, I'm sorry, where did that 1/2 come from? That second one?
So the derivative of x is 1.
Uh-huh.
And then x over 2, so this is going to be x over 2 times the derivative of ln x. What's the derivative of ln x? 1 over x. Die. 1/2. Yeah.
Okay.
Cool.
Okay. Thank you.
Sure. So let's do one that's a little more interesting. Here we go. So that's just a lesson in, if you can simplify the function first, do it, because then derivation would be a lot easier. Yeah, I'll do that. What about this one? Find y prime for that guy. That's so cool. Oh, shit. Okay, so this one gets really interesting. So you take ln, the ln x comes down in front of ln sine x. And then you take derivatives, so you get 1 over y prime equals 1 over x, ln sine x, plus ln x over sine x times, this is going to be chain rule, right? Cosine x. I like it. So you get, let's see, 1 over y prime equals ln sine x over x plus ln x cotangent x. And then you just multiply this thing, right? That's what y is. Multiply that on that side. Ln sine x over x sine x to the ln x plus ln x cotangent x sine x to the ln x. Funky shit. You guys okay with that? Okay. I love the look on your faces. Like, who convinced me to take summer calculus? Shit. You gotta, I mean, come on, on some level, you gotta like this. This is nice. It's really neat. There's no other way to do this derivative, so thank God implicit differentiation works. That opens the door to a lot of shit we couldn't do before, and you're like, why didn't we leave that door closer? Let's see, is there anything else freaky in here? No. Oh, here's one little thing. I always forget about this. One other place you would use the natural log to help you, possibly, is if I had, if I had this kind of thing. It's the same idea, really. I mean, here's an example. Just cut to the chase a little bit here. Okay, do we all agree that's rather disgusting? Yes. Just to show you, I mean, there's flexibility, there's positives and negatives to doing this. It depends on where you want to end up. It depends on what you want to do with it. But if you did take natural log of both sides, what would happen? All this shit, right? Then you can use properties of logarithms, right? So the ln of all this shit would be the ln of x to the 3/4. You guys remember how this works, right, with logarithms? What's the ln of a times b? It's the ln of a plus the ln of b. So I'm going to have plus the ln of x squared plus 1, 1/2, minus, because this is divided by, ln of 3x plus 2 to the 5th. And then notice all the powers can just come down. Become a 3. Whew. And so this derivative becomes relatively simple. You guys see that? Because the derivative of that is just going to be 3/4 times 1 over x. 1/2 times 1 over x squared plus 1 times 2x, the derivative of the inside. 5 times 1 over 3x plus 2 times 3, the derivative means the chain rule, right? Natural log derivatives are relatively simple. 1 over this shit on the inside times the derivative of the shit on the inside. Chain rule. So this would be 1 over y times y prime as always. 3 over 4x plus 1/2 over x squared plus 1 times 2x. So the 1/2 of 2x is x. Minus 5 over 3x plus 2 times 3. Boop. So then you just multiply by this stuff. Bam. So if all you're doing is plugging points in to get derivatives at those points, you don't want to do this directly. You just want to get here, bam, that's quick. Multiply by all this shit, bam, and then you just plug shit in for x. You get what you need, right? If that's all you need to do. So pretty cool with here to here. And then everybody cool from here to here. All I did was take the powers down. Of course, that's another property of logarithms. Probably the most important property. And then the derivatives of ln's are pretty straightforward. I'll tell you one. All right, is that cool? Any questions on that? One derivative we haven't talked about yet is related to like the derivative of 4 to the x, 5 to the x. Derivative of e to the x is easy. Derivative of ln of x is easy. What's the derivative of log base 7 of x? I mean, you're like, you haven't shown us yet, man. Shit, are you really asking me that? Or no, I'm just, it's hypothetical here. It's we don't know, so let's find out. So here, can you guys figure out a way? Yes, you can. In fact, let's just make it log base a of x. Do it. We don't know what it is, so we have to be able to rewrite it.
So, sorry, for the second one, the one on the right side, where'd you get x over?
So it'd be like 1/2, 1 over this,
Right.
times the derivative of the inside, which is 2x. Yeah, and then the 2 and then 1/2 cancel. Okay. How do we figure out the derivative of ln? Didn't we rewrite the logarithm in exponential form? Okay. Here's where we gotta be careful now. Derivative of x is derivative of a to the y. Derivative of a to the anything is a to the thing times natural log of the base, but then you have a y inside, so you better multiply that by y prime. What was a to the y? So you get 1 equals x ln a y prime. So you get y prime is 1 over x ln a. So if you see if it's ln, what's the base of ln, of course? Understood to be e. ln of e is 1. So that's why the derivative of ln is just 1 over x. Derivative of log base 2 is 1 over x with ln of 2 on the bottom. So what's the derivative of a to the x again? I want you to see this. It's a to the x times ln a. You become an ln. There you go, Jeff. What's the derivative of log base a of x? It's going to be 1 over x ln a. That little adjustment, that little, the amount that the slope is off by, it's based on the base according to that ln thing that we keep talking about. You multiply by it for exponential. Logarithms are the inverse of exponential, so it makes so much damn sense that that ends up on the bottom instead of on the top. I'm hoping it does. It does to me. So how would you do here? What would this derivative, the derivative of this function here, if I had f of x equals log base 11 of x squared minus 4x, what would its derivative be? So we gotta be careful. See, the derivative of log base 11 of anything would be 1 over that thing, ln 11. So this is starting off as 1 over that thing, ln 11. See, if it was ln, it would just be 1 over that thing. So any other log base is going to have that piece to it, and then the stupid little adjustment. Oh yeah, your slope's off. Let me help you out there. And then I'm not done, right? Times through the inside. So I get, well, no, in this case you can't. 2x minus 4 over x squared minus 4x, ln 11. Nothing cancels in these two, but sometimes it might. You just got to check. How are we doing there? So it seems kind of silly to say, but just make sure you guys understand, chain rule is not bound to any specific function. It is just a thing that has to be done if something's inside something else, right? It's not bound to any specific function. Yes?
What does the very last line say? It's x squared minus 1 over x, right? The very last line. Yeah. X squared minus 1 over x.
No. X squared minus 4x.
couldn't really read it.
I locked it. Okay. So we can devote the rest of the day to review. You guys, we can look at anything specific you want to. We can look at stuff on the practice test. I'm not going to give you the answer key yet, just because I try to trick you into staying and getting what you need. Yes?
For the X, Aloy, would you mind just going over that one more time? I'm kind of lost.
This here?
Yeah, I'm a little lost on that.
So from here to here, is that cool? Because that's the idea of a logarithm is a to the y equals x. Okay, I like this. That's a way to rewrite logarithm in exponential form. Then I do implicit differentiation. D by dx of x is 1. A to the something is a to that thing times the ln of that base. And then times the derivative of the inside. That's chain rule. And that's what I want. I want to know what y prime is. So then I realize that a to the y is x from the beginning here.
Okay.
And then I can solve for y prime.
Okay.
Yeah.
Thank you.
So whenever you do implicit, you're eventually going to use this idea somewhere in here. Right? We did that before. You have a y, but no, it's really this. It's really what it was from the beginning. In this case, it's a to the y. Oh, it's really x. Oh, sweet. Okay, good. We don't want y dependence over here, really. We want x dependence.
So, going back to like the homework on 3-4, number 65, it has like a graph you want to see the
Yeah.
So when you're trying to find, when you just find the slope, you can just like literally just like count it, right? Count the rise over the run for the slope for like f and g.
The key to this one is they tell you that the first thing I would do for this problem is take derivatives of the functions they gave me.
Yeah.
I could do that before they even show me the graph, right?
Yeah.
So they tell me that u of x is f of g of x.
Yeah. We have f prime,
So u prime of x, yeah,
f prime.
f prime of g of x times g prime of x, right? That's the chain rule, right?
Yeah.
Derivative of f with g of x in it. That's like this. Derivative of a log is 1 over the thing, so it's got that in it, and then the inside gets a term. So when they ask me, the first question is, what's u prime of 1? And the graph they give me has got f doing weird shit and g doing weird shit. I see the slope of g at 1, and then I got to figure out what g of 1 is, right? If I want u prime of 1, that's going to be the slope of f at whatever the shit g of 1 is, times the slope of g at 1. So I got to figure out what g of 1 is, and then I can see this, what's the slope of f at that point, times the slope of g at 1. So I don't know if you guys have seen that problem yet. This is 65 on 3-4. About 6.5. So that's the trick there, is to do the derivative first, and then you're only just plugging that point in, that number. Yep. And the graphs they give you are nice line segments. So it's beautiful. So it's easy to get the slopes. Nothing freaky. Curves are always like, oh shit. Straight lines, you're like, yay. Yes, sir.
So for the practice test, question 5, are we just proving that as that function approaches pi on the x values, that it does hit the limits? Or we're just proving?
Yeah, but specifically using the squeeze there.
Right.
Yeah.
Do you want an example of this?
Well, look at that problem. Which piece of that is oscillatory? Which piece of that is bounded? Which piece of that thing inside the limit is bounded?
Sine.
The sine piece, right? So for number 5, right? So the sine piece is bounded. What's the sine piece bounded between? All right, so you write that. -1, less than or equal to sine of shit, 3 over x minus 5, less than or equal to 1. Now, is that the function I'm actually looking at? No. So then I multiply by the piece I'm missing. Then it's the limit of all 3 sides, and the limit of the outsides are going to be 0, which squeezes the middle to have to be 0, right? If 0 is less than me, is less than or equal to 0, then I'm freaking 0. There's nothing else I could be. You know? Terminator. It's like a hydraulic press. Oh, I'm dead. Squeeze it. Yeah. This one, yeah, there's a few repetitive things on here, which is nice, and that's why it's a little longer than the real test is going to be. The real test is going to be very, it's got to be, it can't be this long. So if you feel like you're like, I did something like that before on this, then yes, you're right. So I'm trying to attack you with a few different ways, some of the same idea.
So, what should we be used to not use our calculator for, in case you do the?
So you've got on the website is the trig thing that tells you what you need to know. Everybody aware of that? On the website, there's a little trig handout that tells you what you need to know, right? So those are the things I'm going to feel completely free just to make you use without telling you what they are.
Oh.
Yeah, so all those identities on that sheet, you have to know, you have to be ready to use. Yeah. And I as somebody who's in the education establishment, I apologize to you if your pre-calc or trig teacher never made you remember some of those things. You should go find them and slap them in the face, right? And say, what the shit is wrong with you? Right? You have pre-calculus, you're supposed to